7.3 notes. Today we're talking about transformations, different types of transformations, and also transformation notation. Notation simply means how do you write something? So how do we write these different transformations in algebra? Think of algebra as like a different language. So how can we write what these transformations look like in algebra? What do they look like? How do we write it? That's what notation is. Essential question, you should be writing this down as always. Stop right here. So if you guys have not watched the video that I posted in the 7.2 Canvas notes assignment before this video, two different videos, you need to go watch that video and take notes on that video before you do this notes video. And then just combine the two together as one notes assignment. But make sure that you watch that video first before coming to this one. So if you haven't, do that now. And pause this. Remember, you guys can pause at any time and rewind if I'm going too fast. Transformations. So these need to get all in your notes. These are the different transformations that you watched in the video that I asked you to watch before this one. First transformation is a translation, and here's how you write it in algebra. The translation is you have an XY coordinate. This arrow sign is indicating that there is some type of transformation happening. And then here's what's happening to your X and Y coordinates. So you are adding or subtracting some value A to the X coordinate. So in a translation, a figure could be sliding left or right, right? So if it's sliding to the right, you are adding some value to X because that's the X-axis is the horizontal axis, left and right? So if you're adding something to the X value, it's going to be sliding right. If you are subtracting something from the X value, it's going to be sliding to the left. Similarly with the Y value, except the Y-axis is vertical up and down, if the figure is sliding up, you are adding some value B to that Y coordinate. If the figure is sliding down, you are subtracting some value from that Y coordinate. Depending on how much it is sliding up or down. If it's sliding 6 units up, you would be adding 6. If it's sliding 6 units down, you would be subtracting 6. Same thing goes for the X value as well. In a dilation, we already talked about this in the last notes video, so I won't be covering too much of that, but that's in the 7.1 video, dilations. Reflection across the X-axis. You have your original XY coordinate. Again, arrow is a transformation that's happening, and what happens is the X value stays the same, but the Y value switches to the opposite. So if the Y value is negative, it becomes positive. If it's positive, it becomes negative. And that's the only thing that happens to the coordinate if you're reflecting across the X-axis. Reflecting across the Y-axis, these are both reflections, just this one's across the X-axis, this one's across the Y-axis. XY coordinate, transformation. The X coordinate is the opposite this time, and the Y coordinate stays the same. So these are pretty similar, so you need to understand the difference. I know it seems weird that when you reflect across the Y-axis, X changes, and when you reflect across the X-axis, Y changes. And we'll talk more about that in future assignments and notes. A rotation, so the last transformation is a rotation. So we've covered a translation, a dilation, and a reflection. The last one is a rotation, and here are 3 different types of rotations that happens, and then notation. On a 90 degrees clockwise, remember clockwise is this way, like a clock. So if we rotate 90 degrees, that's 1/4 of a circle. Your original XY coordinate, transformation, the X and Y, see how they have switched spots, and X has changed to the opposite value. In a rotation 90 degrees counterclockwise, so that's like this, opposite of a clock, you have your original XY, arrow means a transformation's happening, X and Y switch again, but this time Y is the opposite. And then finally in a 180 degree rotation, if you think about it, a 180 degree rotation is the same thing as 2 90 degree clockwise rotations. It's also the same thing as 2 90 degrees counterclockwise rotations. So rotation 180 is original XY. Notice how If I rotated it 90, X and Y would change, right? But if I rotated it another 90, X and Y would change back to where they originally were. So in a rotation 180, they're in the same exact spot. See how it's X, Y, but they're both opposite. That's a 180-degree rotation. Pause and rewind as needed. So let's go over some examples here. Complete the transformation. So it says you have a triangle here with these coordinates. A, B, and C are the points, and here are the coordinates of each of those points. So in number 1, it says you have your original XY coordinate, and it looks like they're saying add 2 and subtract 4 from Y. Add 2 to X, subtract 4 from Y. What type of transformation is that going to be? Go back and look at your notes if you need to, and pause this video. Hopefully you said that would be a translation. So this is definitely a translation because you can see we're adding and subtracting values from the X and Y coordinate, which tells us that that's a translation. It's sliding. So all I need to do is add 2 to every X, right? So I'm going to write A, B, and I'm going to put C up here so I have room. So the original A coordinate, A. So every X coordinate, I'm going to add 2. 4 plus 2, 6. 4 plus 2, 6. Negative 2 plus 2, 0. And then every Y coordinate, I'm going to subtract 4, like it says. Every Y coordinate, subtract 4. 2 minus 4, negative 2. Negative 2 minus 4, negative 6. Negative 2 minus 4, negative 6 again. And then you have your 3 new points of the translated image that you could graph. You don't have to graph for this one, but that's what you would graph if you were supposed to graph. What's the second transformation going to be? Pause the video and answer. Hopefully you said that this is a dilation. You would be correct. How do we know that? It's because we are multiplying X and Y by some factor, K. So this tells us that our scale factor is 1/2, which means this is a dilation, and it will be a reduction because we're multiplying by a scale factor that is less than 1 but greater than 0. So it's saying take every X and Y coordinate and multiply them by 1/2, which is the same thing as dividing by 2. So I'm going to write A coordinate, B coordinate, C. And you know what? I should be writing A prime, B prime, C prime. I forgot to do that on the first one because these are my new image coordinates. So 4, 2, 4 times 1/2 is 2. 2 times 1/2 is 1. On B prime, 4 times 1/2 is 2. Negative 2 times 1/2, negative 1. On C prime, negative 2 times 1/2, negative 1. And negative 2 times 1/2, negative 1. And those are your new prime coordinates of the image. That would be a dilation because you're multiplying X and Y by some scale factor, which in this case is 1/2. What's the third one going to be? Pause the video and think about it. Go back and look at your notes from the previous slide if you need to. So hopefully you see that what? X and Y, they're staying in the same spot, but Y is the opposite. So that tells us it's a reflection across the x-axis. So this is a reflection x-axis. So let's write our new A prime, B prime, and C prime coordinates. So all I'm going to do is keep X and Y in the same exact spot. So X never changes, so I'm just going to write the same X value, 4, 4, and negative 2. But you can see that Y is the opposite. So instead of 2, it's negative 2. Instead of negative 2, it's positive 2. And instead of negative 2, it's positive 2. So I'm going to write negative 2, positive 2, positive 2. And I have my new prime coordinates for the image. And this would be a reflection across the x-axis. Here's example 4. Go ahead and pause the video and sketch this example. Graph paper would be extremely helpful, obviously. You guys should be using graph paper. And then click continue and you're ready. So what we need to do here, it says prove the two shapes are similar. PI means this is the pre-image. This is the original figure. And then here is the image. So to prove that they're similar, we need to prove that there was some sort of sequence of transformations that happened to map this exactly onto this. So you can see that the original figure is bigger than the smaller one, but I think with some sort of dilation, we can get it to be the same size. Let's count how long the length of this side. So if I count it, it's 1, 2, 3, 4, 5, 6, 7, 8. If I count this one, it's 1, 2, 3, 4. So if I go from 8 to 4, that tells me that 1/2 is the scale factor, right? 8 times 1/2 is 4. So if I dilate this figure by 1/2, I'm going to get it to be the same size. So let's go ahead and mark these coordinates. Let's call this A, B, and C. And then here's my y-axis. So it looks like here's the origin right here. A's coordinates are going to be 1, 2, 3, 4. Go ahead and mark the other 3 coordinates as well. We've marked the coordinates of the 3 points. Okay, we're just going to multiply them all by 1/2. Go ahead and multiply all those coordinates by 1/2, and let's see what we get. Now we've multiplied all the coordinates by 1/2. Remember, multiplying by 1/2 is the same divided by 2. So 0 times 1/2 is still 0. 4 times 1/2 is 2. And then see how these are just divided by 2. So this is my new dilated figure here. And you can see it's the same size as this one, right? So all I need to do now is slide it, it looks like, to the right and maybe down a little bit. Figure out how much I need to slide it right and down a little bit. Hopefully you can see that all we need to do is slide it, 1, 2, 3, 4, 5, 6 to the right and down 1. And then therefore it would be right on top of this figure, therefore proving that the shapes are similar. So how we write that is we can write the first transformation was a dilation of 1/2. How do I write that? Like this. Remember, we just multiplied every xy coordinate by 1/2. And then what did we do? We slid it, a translation, right 6. So I say x plus 6 and down 1, y minus 1. And that's how you write the language of what we just did. Last example for your notes here, we're doing the same exact type of thing. We're proving that the shapes are similar. Pause the video and make sure that you sketch this nicely on graph paper in your notes. Here's the pre-image and here's the image, the original figure, new figure. So you can see that they're the same size, so we don't need to do a dilation, but it looks like we definitely need to rotate it and maybe slide it, right? Because we needed to get it to be the same orientation because it's not. So I'm going to rotate this 90 degrees. You can see it's in this quadrant here. Here's quadrant 1, quadrant 2, quadrant 3, and quadrant 4. If I'm in quadrant 2, I just need to rotate it 90 degrees this way. So when I rotate it 90 degrees clockwise, it'll end up over here. You could rotate it 90 degrees counterclockwise and it would end up here. The problem is it would be upside down, right? I need to rotate this way so it's the same orientation. So go look to see what happens to the coordinates when we rotate it 90 degrees clockwise. Hopefully you saw that all you have to do to rotate 90 is flip the x and y coordinates, and then you need to change the x coordinate to the opposite. So for example, A, if I flip it, it becomes 1, -5, but then your x coordinate needs to change to the opposite, so it becomes 1, 5. That's why 1, 5 ends up here. Also, here's a hint. If you're rotating 90 degrees clockwise, that you know you're going to be in quadrant 1. And in quadrant 1, x and y are always positive, right? So you don't really have to remember the signs too much if you know what quadrant you're going to be in. Okay, if you know you're in quadrant 1, x and y will be positive. If you know you're in 2, x is negative, y is positive, and so forth, right? So same goes for b prime and c prime. See how that works? Now you can see we're at the same orientation here. So now it looks like all I need to do is just slide it. So let's look at point C right here. Let's see how far I need to go down. 1, 2, 3, 4, 5, 6, 7 down, and then what? 1, 2 to the right. So to finish this off, we would say the first transformation that happened is a rotation of 90 degrees, which the notation looks like this. What did we do? We switched x and y, and then x became opposite, right? That's how you write it. And then secondly, we translated, which means original xy, and then we went right 2 and down 7, right? Right 2 and down 7. So x plus 2 and y minus 7. And that's how you're proving that the shapes are similar, by some series of transformations, 2 transformations that put one shape exactly on top of the other shape. That is the end of your notes. As always, write a summary and do well on it.